So I'm not a native speaker, and I was wondering what a flash talk might be. This is a new invention. I thought this was going to be a poster. So I asked around, and I was told that it had to do with Flash Gordon, right? It's a voice name, but not quite. Then I asked Enrique, who's just coming in, and he told me that this is where your conclusions go up in the next slide. And that's really a flash talk, but you're out of luck. I have infinitely many more.
Flash Gordon is relative of Flash Gordon.
Alright, so this is about this plot. We have here two variables, rapidity and azimuth. Okay? And I put it against the Alice detector, and you see here rapidity is the variable that pushes you along the beam axis, and azimuth is around the wheel. Okay? So these are these two variables, and what's being plotted is two particle correlations. Yes? So two postdocs like each other and come out of that same door talking. That's correlated. Two old grumpy professors who are not citing each other anymore come out by the separate doors. Okay? That's anticorrelated. So here we see a very nice forward correlation peak, and which is the two postdocs coming out together, and a small anticorrelated peak, which is the professors coming out by different doors. Yeah? So these are back-to-back jets, and this comes from the same jet. And there is a lot of other structure that's too complicated. So what we're going to do is to project everything on the azimuthal variable and make a 2D plot, which is this. The Alice data for these correlations, in this case it's K plus K plus correlation, same charge, is this gray box, these gray boxes here. And everything else is various Monte Carlo simulations, but everything's more or less right. So then that's the flash talk, we finished. Not quite. Because these people in Warsaw had the idea of looking, because Alice can separate particle ID very well, they started of looking at baryons. So they did proton-proton correlations. And now we see that phi equals 0, which is the postdocs coming out together on the same door, is totally depleted. Okay? However, the Monte Carlo is qualitatively off. This is a gross disagreement between theory and experiment. Okay? So this is what we were looking at. Well, you could think, right, these guys are fermions, so they tend to separate, except, so they're undistinguishable fermions, right? Except they tried again with proton lambda and they saw the same effect. So this has to go back, maybe to the quark level, and we set out to explore it a bit in Madrid. Very good. It's out in the archive, it's not published yet. Basically what we did was open Pythia, go back to the fragmentation thing that underlies this Monte Carlo. So you have a string, create a quark-antiquark pair, and that turns it to two strings. Then you can create a diquark-anti-diquark pair, and you have two more strings. You keep going down, and you start having things that look like mesons or baryons. And eventually, after this has exhausted the mass, this conference is about mass generation. Well, officially, mass generation is whatever is in Pythia. Yes. Eventually, you collect your mesons and baryons when there's no energy left. And now you read what happened. Okay. Very good. So we looked, we did that toy and looked at string correlations. So this is a purely theoretical thing which is not observable, but just to learn if the anticorrelation was we were getting it wrong from them. So this is the correlation between two strings, again in rapidity and azimuth, and you can see that there is a huge ridge here. So it's basically isotropic in azimuth, and then there's a kind of something here in the middle. Right? It's back to back, and not much at 0. Okay, so it's basically not coming from there. And here there is a similar story, and it's too complicated I have to explain it in full. But then we went to look at the correlation between two baryons coming from the same string, and bingo, that does it. Here are two baryons coming out of the same string, and you have a beautiful peak at phi equals 0. That's actually the peak that's causing the disagreement with experiment. So it is a theory problem. These Monte Carlo simulations are not taking into account either the Pauli-principle at the quark level or something. Okay? So we tried a toy simulation to check it, and what we did is to apply a one-baryon policy. Yeah? This means that each string can only father one baryon, so no string can split in two. Now this eliminates the positive correlation between baryons very nicely, but in exchange it depresses the total baryon number, because many baryons were coming from the same string. So what we did then was to apply an always-baryon policy. Every string must produce one baryon. Then baryons remain anticorrelated, and now their abundance is okay. Very good. That's the three-dimensional plot. You don't see a peak at 0 angle, and however, now you see that the agreement between the simulation and the data is very good. Now that's a toy model, and there's no reason why physics should apply a one-baryon policy or whatever, but this means that the developers of Pythia should be thinking about how to spread baryon production, which is our conclusion. Okay. Thank you.
Just one question for Felipe, if you want.